This video is audio content only. It does not contain any video footage or images. If you are expecting visual content, please be aware. This is intentionally provided in an audio-only format. We recommend listening to the audio rather than watching the screen. Thank you for your understanding. Welcome. Today, we're diving into one of the most fascinating puzzles in physics and mathematics, the three-body problem. For centuries, scientists have grappled with a deceptively simple question. Can we predict the motion of three celestial objects orbiting each other? While two bodies dance predictably, adding just one more creates beautiful chaos. Join us as we explore why this problem captivated Newton, stumped generations of mathematicians, and continues to reveal surprising secrets about our universe today. Chapter 1. Newton's triumph meets the impossibility of three. In 1687, Isaac Newton published what would become one of the most transformative equations in human history. His universal law of gravitation stated that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The equation itself was deceptively simple, elegant in its mathematical brevity. Yet this single formula allowed humanity to unlock the clockwork mechanics of the heavens. Newton's triumph was immediately apparent in the two-body problem. Take the Earth and the Sun, two massive objects exerting gravitational force on one another. Armed with his law, Newton could predict with stunning accuracy how Earth would orbit the Sun. The calculations revealed a stable, repeating pattern. Earth completes its journey around our star in approximately 365.24 days, what we call a solar year. This isn't an approximation or a guess. It's a mathematical certainty derived from the fundamental forces governing these two bodies. The same precision applied to the Moon orbiting Earth. Every 27.3 days, our natural satellite completes its circuit. Again, the two-body solution provided exact answers. Newton could peer into the future and tell you precisely where the Moon would be in relation to Earth on any given date, years, or even centuries ahead. The mathematics didn't merely describe what was happening. It predicted what would happen with an accuracy that seemed almost miraculous to his contemporaries. This predictive power represented something profound. For millennia, humans had watched the heavens with a mixture of awe and confusion. The planets wandered across the sky in patterns that seemed sometimes regular, sometimes bewildering. Comets appeared without warning, inspiring dread and superstition. The moon's phases and eclipses could be roughly anticipated, but the underlying why remained mysterious. Newton's equations transformed this cosmic uncertainty into mathematical certainty. The two-body solution worked because the mathematics remained tractable. When you have only two objects exerting gravitational influence on each other, the differential equations describing their motion can be solved exactly. Mathematicians call this an integrable system. You can write down a formula that gives you the position and velocity of both bodies at any point in time, past or future. The orbits are conic sections, ellipses in most cases, and these ellipses remain stable and predictable indefinitely. But the universe rarely limits itself to pairs. Our solar system doesn't consist of just the Sun and Earth, or just Earth and the Moon. Multiple planets orbit our star. Moons circle planets. The gravitational influence of Jupiter tugs on Mars. Saturn's mass affects Earth, however slightly. Every body in the solar system exerts force on every other body. Newton knew this, of course. His equations described the gravitational force between any two masses, but applying them to multiple bodies simultaneously created a very different mathematical landscape. Enter the third body, and everything changes. Not gradually or subtly, but fundamentally and catastrophically from a mathematical perspective. The three-body problem asks a seemingly simple question. If you have three masses in space, each exerting gravitational force on the other two, can you predict their future positions and velocities? Can you write down equations that solve for their trajectories the way Newton solved the two-body problem? The answer, discovered through centuries of mathematical struggle, is no. There is no general solution to the three-body problem. You cannot write down a formula in terms of a finite number of standard mathematical operations that tells you where three gravitationally interacting bodies will be at any future time for arbitrary initial conditions. This isn't because mathematicians haven't been clever enough. It's because such a solution fundamentally does not exist. This revelation came gradually and painfully. In 1767, Leonhard Euler, one of history's most prolific mathematicians, found three families of periodic solutions to the three-body problem. In these special cases, the three masses remain prolinear at each instant, meaning they stay in a straight line as they move. These solutions were real and mathematically valid, but they represented an infinitesimally small subset of all possible configurations. Imagine all the ways three objects could be positioned and moving in three-dimensional space. Euler's solutions were like finding 3 grains of sand on all the beaches of Earth. Remarkable discoveries, certainly, but they highlighted how vast the unsolved territory remained. 5 years later, in 1772, Joseph Louis Lagrange discovered another family of solutions. In his configuration, the three masses form an equilateral triangle at all times. The triangle might rotate or change size, but it maintains its equilateral geometry. These became known as Lagrange points, and they have practical applications even today. The James Webb Space Telescope sits at the L2 Lagrange point of the Earth-Sun system, maintaining a stable position relative to both bodies. These discoveries were tantalizing but frustrating. They proved that some three-body configurations were solvable, but they were special cases requiring precise initial conditions. What about all the other possible arrangements? What about three bodies positioned randomly in space with arbitrary velocities? The general solution remained elusive. Throughout the 18th and 19th centuries, mathematicians attacked the problem from every angle. They developed new mathematical tools, invented novel approaches, and discovered intricate relationships between the conserved quantities in the system. Energy is conserved in the three-body problem. So is momentum and angular momentum. These conservation laws constrain the motion, providing some limitations on what the bodies can do. The nonlinearity of the gravitational force creates feedback loops of mathematical complexity when three bodies interact. The force each one experiences depends on the positions of the other two, which in turn depend on the forces they experience, which depend on positions. The differential equations describing this system cannot be integrated in closed form, except for those rare special cases Euler and Lagrange discovered. Mathematicians proved that singularities in the three-body problem correspond to collisions between bodies. Binary collisions occur when two bodies crash into each other. Triple collisions happen when all three bodies meet at a single point simultaneously, though this only occurs when angular momentum equals 0, making such events exceedingly rare for generic initial conditions. In the 20th century, mathematicians discovered thousands of periodic three-body solutions using computer simulations, each representing stable configurations where bodies trace repeating paths. But these solutions remain vanishingly rare among all possible configurations. The three-body problem thus stands as a monument to the limits of mathematical knowledge. Newton gave us equations that perfectly describe gravitational interaction. These equations are exact, not approximations. Yet for three or more bodies, those exact equations yield no general analytical solution. We can compute numerical approximations for specific cases. We've discovered special periodic solutions. But the general problem remains unsolved and fundamentally unsolvable. Not every well-posed mathematical question has a clean answer expressible in familiar functions. Some systems resist solution, not because we lack cleverness, but because the nature of the equations themselves forbids it. Our own solar system is, of course, an N-body problem with 8 planets, numerous moons, asteroids, and comets. Newton's two-body solutions are approximations, useful because the Sun's mass dominates and the planets' gravitational influences on each other are relatively small. But they do influence each other, and over long enough timescales, complex interactions emerge from these mutual perturbations.
The gap between 2 bodies and 3 bodies represents a chasm in mathematical complexity, one that centuries of brilliant effort have failed to bridge. Adding just one more body transforms a perfectly solvable system into one that generically defies analytical solution. The elegant predictability of Newtonian mechanics, so triumphant in the 2-body case, encounters a fundamental barrier with 3 bodies. This distinction reveals something profound about the structure of mathematics and physics. The same gravitational force that yields perfect solutions for 2 bodies creates insolvable complexity for 3. The equations remain exact, the physics remains deterministic, yet the mathematics refuses to provide the analytical tools that worked so beautifully for pairs. When Newton published his universal law of gravitation in 1687, he opened a door to understanding the cosmos. The 2-body problem walked through that door into a realm of perfect predictability and elegant mathematical solutions. But the 3-body problem stopped at the threshold, forever resisting entry, forever remaining just beyond the reach of analytical mathematics. That resistance, that fundamental impossibility, would prove just as important to science as Newton's original triumph. It forced humanity to confront a universe more subtle and more complex than the clockwork mechanism we first imagined. The 3-body problem stands as a permanent reminder that mathematical elegance has limits, that some questions resist answers not from lack of effort, but from the deep structure of the equations themselves. The universe follows precise laws, but those laws don't always yield to human desires for closed-form solutions and perfect prediction.
Chapter 2. Chaos Theory's Dark Revelation. In 1889, Henri Poincaré sat at his desk in Paris, staring at a paper that was about to destroy his reputation before he could salvage it with one of the most important discoveries in the history of mathematics. He had just won a prestigious prize from King Oscar II of Sweden and Norway for his work on the stability of the solar system. The memoir had been published, praise had been showered upon him, and then he found the error. A significant, fundamental error that undermined his conclusions. Most mathematicians would have been devastated. Poincaré instead saw an opportunity that would reshape our understanding of the universe itself. Working to correct his mistake, he stumbled upon something far more profound than the prize-winning result he'd been trying to fix. He discovered that the 3-body problem, and by extension much of the cosmos, exhibited a property so counterintuitive, so philosophically unsettling, that it would take decades for the scientific community to fully grasp its implications. That property was chaos. But chaos, in the mathematical sense, means something very different from its everyday usage. When we say a room is chaotic, we mean it's messy, disorganized, random. Mathematical chaos is none of these things. A chaotic system is completely deterministic. There's no randomness whatsoever in the equations governing its behavior. Given identical starting conditions, a chaotic system will always evolve in exactly the same way. The same inputs always produce the same outputs. The equations are precise, the physics is exact, and yet, paradoxically, long-term prediction becomes impossible. This impossibility arises from what mathematicians call sensitive dependence on initial conditions. Take 2 chaotic systems that are nearly identical. The difference between them is infinitesimal, far smaller than any measuring instrument could detect. Perhaps one particle is displaced by a distance smaller than an atomic nucleus. Perhaps one velocity differs in the 20th decimal place. These systems start out so similar that they're effectively indistinguishable. Yet, as time passes, this microscopic difference grows. At first, slowly, almost imperceptibly, but then exponentially. After enough time, the two systems bear no resemblance to each other whatsoever. This is what Poincaré discovered lurking in the equations of celestial mechanics. The three-body problem was his laboratory, the place where this strange behavior first revealed itself to human understanding. And the discovery emerged from profound mathematical theorems that would reshape our knowledge of what's possible in physics. Mathematicians had been searching for additional conserved quantities in the three-body problem, properties beyond the classical ones that might unlock a solution. If there were just one or two more quantities that remained constant, perhaps those would provide the missing constraints needed to integrate the equations.
Heinrich Bruns destroyed that hope. In the late 19th century, he proved a remarkable theorem, stating there are no more algebraic conserved quantities in the three-body problem beyond the classical ones. An algebraic conserved quantity would be some combination of the positions, velocities, and masses that could be expressed as a polynomial or algebraic function and that remained constant over time. Bruns proved mathematically that no such quantity exists. He didn't just fail to find one, he proved that the search was futile, that no amount of cleverness or persistence would ever uncover additional algebraic conserved quantities because they simply don't exist. This was a devastating result, but Poincaré went further. He proved that there are no more analytic conserved quantities either. Analytic functions are more general than algebraic ones. They include power series, exponentials, logarithms, trigonometric functions, and combinations thereof. Poincaré's theorem was stronger than Bruns. It said that you cannot find any new conserved quantity expressible as an analytic function of the positions and velocities. There are no hidden constraints waiting to be discovered that would make the problem solvable. This was a devastating result, but Poincaré went further. He proved that there are no more analytic conserved quantities either. Analytic functions are more general than algebraic ones. They include power series, exponentials, logarithms, trigonometric functions, and combinations thereof. Poincaré's theorem was stronger than Bruns. It said that you cannot find any new conserved quantity expressible as an analytic function of the positions and velocities. There are no hidden constraints waiting to be discovered that would make the problem solvable. These theorems were mathematical achievements of the highest order, but they revealed something troubling. The dimension of the phase space, the mathematical space describing all possible states of the system, exceeds the number of constraints. This dimensional mismatch means the system is not integrable. An integrable system is one where the number of conserved quantities equals the number of degrees of freedom, allowing you to solve the equations exactly. The three-body problem has too much freedom, too many dimensions in which it can wander, and not enough constraints to pin down its behavior. The system is under-constrained, and this lack of constraint opens the door to chaos. But Poincaré found something even more disturbing than non-integrability. The trajectories themselves exhibited sensitive dependence on initial conditions. To understand what this means, imagine you're tracking the motion of three stars gravitationally bound to each other. You measure their current positions and velocities as precisely as your instruments allow. These measurements have some uncertainty. No instrument is perfect. Perhaps you know each position to within a millimeter and each velocity to within a millimeter per second. You plug these measurements into Newton's equations and compute forward in time. For a while, your predictions match reality beautifully. You can predict where each star will be in a week, a month, even a year. But gradually, your predictions start to diverge from observations. The divergence is small at first, just slightly outside your measurement error, but it grows. After a few more orbits, the predictions are wildly off. Eventually, your calculations show the stars in completely different positions than where they actually are. The natural assumption would be that you need more precise measurements. If you could just measure the initial conditions more accurately, your predictions would stay accurate for longer. This assumption is correct, but it misses the deeper point.
Yes, better measurements extend the prediction horizon. If you improve your precision by a factor of 10, you might be able to predict 10 times further into the future. But there's a fundamental limit. No matter how precisely you measure, eventually the predictions fail. And because the errors grow exponentially, improving your measurement precision only linearly extends your prediction horizon. This is the heart of chaos. The deterministic equations guarantee that if you knew the initial conditions perfectly, with infinite precision, you could predict infinitely far into the future. But perfect knowledge is impossible. Physical measurements always have finite precision. The universe itself imposes limits through quantum mechanics. And even if you could measure with arbitrary precision, the slightest perturbation from a distant star, an asteroid, even a photon of light striking one of the bodies would eventually snowball into large-scale changes. This is the heart of chaos. Poincaré analyzed the phase space of the three-body problem to understand this behavior. Phase space is a mathematical construction where each point represents a complete state of the system. Think of it as a map where every possible configuration and motion of the three bodies corresponds to a single point. For three bodies moving in three-dimensional space, this map requires 18 dimensions, 6 for each body. 3 dimensions specify position, 3 specify velocity. You cannot visualize an 18-dimensional space directly, but mathematicians can still work with it analytically, studying how points move through this abstract landscape as the system evolves. Poincaré studied how trajectories evolve in this phase space and discovered regions where nearby trajectories diverge exponentially. Two states that start arbitrarily close together in phase space follow paths that separate faster and faster. This exponential divergence is the signature of chaos. It means that even infinitesimal uncertainties in the initial state get amplified until they dominate the system's behavior. The mathematical structure underlying this chaos is extraordinarily complex. The phase space contains a tangled web of stable and unstable regions. Some trajectories are periodic, returning to their starting state after a fixed time and repeating the cycle forever. These periodic orbits form a skeleton around which the chaotic trajectories swirl. Near each periodic orbit, there are regions of stability, where trajectories stay close to the periodic solution, and regions of instability, where trajectories spiral away.
The boundaries between these regions are fractal, possessing structure at every scale. Zoom in on a boundary, and you see the same complex, intertwined pattern repeated at smaller scales. Zoom in again, and the pattern repeats. This self-similarity extends infinitely. The geometry of chaos is as beautiful as it is mathematically rigorous, revealing an order within the apparent disorder. But from a practical standpoint, this structure guarantees unpredictability. The fractal boundaries mean that arbitrarily close to any stable trajectory, there are unstable ones, and vice versa. You can never know with certainty which type of region you're in because you can never measure the initial conditions with infinite precision. The system might be on a stable trajectory that will persist for millions of years, or it might be teetering on the edge of instability, ready to veer off into dramatically different behavior. This discovery shattered what physicists called the Laplacian dream, named after Pierre-Simon Laplace, who in 1814 famously wrote that if an intellect knew the precise position and velocity of every atom in the universe and could process this information through the laws of physics, then nothing would be uncertain and the future would be present before its eyes. Laplace envisioned a clockwork universe where perfect knowledge of the present guaranteed perfect knowledge of the future. Poincaré's discovery revealed this vision as fundamentally flawed. Even in a completely deterministic universe governed by precise mathematical laws, perfect knowledge is unattainable, and long-term prediction is impossible. The equations don't contain any randomness. There are no dice being rolled by the gods. The same initial conditions always produce the same outcome. But because we can never know the initial conditions perfectly, and because tiny uncertainties grow exponentially, the future remains shrouded in fundamental unpredictability.
This has profound philosophical implications. It means that determinism and predictability are not the same thing. A system can be completely deterministic, with every event having a cause and the future being entirely determined by the past, and yet remain unpredictable in practice. The laws of physics might be exact, but our knowledge of how those laws will manifest in specific situations is inherently limited. Consider the restricted three-body problem, a simplified version where one of the three masses is negligible compared to the other two. A spacecraft moving in the gravitational field of Earth and the Moon is a classic example. The spacecraft's mass is so small it doesn't affect Earth's or the Moon's orbit, but they certainly affect it. This simplification reduces the complexity, but doesn't eliminate the chaos. The restricted three-body problem has a conserved quantity called the Jacobi integral. It's a combination of the spacecraft's energy and angular momentum that remains constant. This provides one constraint, but the phase space is four-dimensional, so one constraint isn't enough to make the system integrable. The Jacobi integral determines which regions of space the spacecraft can reach, but it doesn't determine a unique trajectory. Depending on the value of the Jacobi integral, radically different behaviors are possible. For some values, a spacecraft initially orbiting Earth might stay in Earth's vicinity forever. For other values, it might be captured by the Moon. For still others, it might be ejected from the Earth-Moon system entirely, escaping through Lagrange points L2 or L3 into a trajectory around the Sun. These transitions between different behaviors occur at critical values of the Jacobi integral. Near these critical values, tiny changes in initial conditions can determine whether the spacecraft stays or escapes. This is chaos manifesting in a practical system. Spacecraft trajectory designers must account for this sensitivity, using it to their advantage when possible. The complex gravitational landscape created by two large bodies offers low-energy pathways between them, but navigating these pathways requires extreme precision. A spacecraft aimed at a lunar trajectory might, with a microscopic adjustment in velocity, end up on a completely different path, perhaps escaping to deep space or crashing into Earth. The discovery of chaos in the three-body problem led to the development of new mathematical tools for studying complex systems. Poincaré invented what's now called the Poincaré section, a technique for visualizing high-dimensional dynamics by taking slices through phase space. Instead of trying to track the full 18-dimensional trajectory, you watch where it intersects a particular surface. For a periodic orbit, the intersection points repeat. For a chaotic orbit, the points fill out complex patterns that reveal the underlying structure. These mathematical innovations weren't just abstract exercises. They fundamentally changed how mathematicians and physicists understood dynamical systems. Before Poincaré, the assumption was that most systems could be solved analytically, and those that couldn't were simply too complicated to bother with. After Poincaré, it became clear that most systems are chaotic, and the ones that can be solved exactly are special exceptions. This realization spread beyond celestial mechanics. Meteorologists discovered that weather is chaotic, with Edward Lorenz's famous butterfly effect arising from similar sensitive dependence on initial conditions. The flap of a butterfly's wings in Brazil might, through a chain of causation, alter the course of a tornado in Texas. Not because the butterfly's impact is large, but because the atmosphere's dynamics amplify small perturbations exponentially. Lorenz found this chaos while running computer simulations of atmospheric convection. When he restarted a simulation using slightly rounded values from a printout, expecting to reproduce the same weather pattern, he instead found the simulation diverged dramatically. This tiny difference, smaller than measurement error in real weather data, spiraled into completely different outcomes. Consider also the double pendulum, a simple mechanical system that demonstrates chaos with stunning visual clarity. Take a pendulum and attach another pendulum to its end. The equations describing this system are deterministic and relatively simple compared to the three-body problem, yet the motion is chaotic. Release two double pendulums from nearly identical starting positions and watch them evolve. At first, they swing in sync. Then small differences emerge. Within seconds, they're moving in completely different patterns. The double pendulum has become a favorite demonstration of chaos because it's so visceral. You can build one in a workshop and witness sensitive dependence on initial conditions with your own eyes. Fluid dynamics, ecology, economics, neuroscience, and countless other fields found chaos lurking in their equations. Wherever you have nonlinear interactions, multiple components influencing each other through feedback loops, chaos becomes possible. And the three-body problem was the first place this chaos was rigorously studied and mathematically understood. The implications for our solar system are sobering. Our planetary system is an 8-body problem at minimum, with additional contributions from moons, asteroids, and comets. The interactions between these bodies create a web of gravitational influences that cannot be solved analytically. Numerical simulations must be used instead, integrating the equations forward step by step. These simulations reveal that the solar system has a chaos horizon extending tens to hundreds of millions of years into the future. Within that time frame, predictions remain reasonably accurate. We can calculate where Earth will be in 10 million years with good confidence. But beyond the chaos horizon, exponentially growing uncertainties make precise prediction impossible. The positions of the planets 100 million years from now are fundamentally unknowable, not because we lack computational power, but because the mathematics is chaotic. This doesn't mean the solar system is unstable. Chaos doesn't imply immediate disaster. Most likely, the planets will continue their stately orbits for billions of years. But the precise details of those orbits, the exact positions at specific future times, cannot be predicted beyond the chaos horizon. And there's a small but non-zero probability of more dramatic changes. Mercury's orbit might become unstable, leading to a collision with Venus or ejection from the solar system. Such events are rare, but they're possible, and we cannot predict when or if they'll occur. Some researchers estimate there are 20 times as many rogue planets wandering the galaxy as there are stars. These orphan worlds, gravitationally unbound to any star, were likely flung from their birth systems by chaotic gravitational interactions. Young solar systems with multiple giant planets in close proximity can experience violent instabilities. Planets scatter off each other, with some settling into stable orbits and others being ejected into interstellar space. This is chaos made manifest on a cosmic scale, the three-body problem playing out in nature and reshaping the architecture of planetary systems. The mathematics doesn't stop at predicting positions. Chaos affects every aspect of complex systems. In some configurations, chaos can be constructive. The mixing it induces can spread heat or nutrients more efficiently than ordered motion would. In other contexts, chaos is destructive, tearing apart structures that would otherwise persist. Even the theoretical solutions that exist for the three-body problem reveal the depth of this unpredictability. Carl Sundman proved in 1912 that a solution exists as an infinite series. This was a remarkable mathematical achievement, proving that the three-body problem is not fundamentally unsolvable in an abstract sense. But the practical impossibility of using this solution became clear when David Billericki calculated in 1930 that if Sundman's series were to be used for astronomical observations, then the computations would involve at least 10 to the power of 8 million terms. This number is so astronomically large that even if you could compute 1 trillion terms per second, the age of the universe wouldn't provide enough time to finish. The theoretical solution exists, but it might as well not exist for any practical purpose. This is chaos theory's dark revelation. The universe is fundamentally unpredictable beyond certain horizons, not because the laws of physics are random or approximate, but because the mathematical structure of those laws guarantees it. Determinism doesn't save us. Precise equations don't guarantee precise predictions. The three-body problem proved this rigorously, mathematically, inescapably. And once you've seen this truth in the stark clarity of Newton's equations applied to three gravitating masses, you begin to see it everywhere, in weather patterns, in ecosystems, in economies, in the beating of hearts and the firing of neurons.
These are different kinds of limits than quantum mechanics imposes. Quantum uncertainty is fundamental to the nature of particles. You cannot simultaneously know a particle's position and momentum with arbitrary precision because the act of measuring one affects the other. Chaos is different. The equations are classical and deterministic. There's no fundamental limit to how precisely you could measure the initial conditions in principle, but in practice you can never measure precisely enough to extend the prediction horizon indefinitely. These two sources of unpredictability, quantum and chaotic, combine in the real universe to create multiple layers of fundamental unknowability. Small-scale quantum fluctuations provide the seeds that chaotic dynamics amplify into large-scale unpredictability. The future is shrouded not just by our ignorance, but by the mathematical structure of reality itself. Poincaré's discovery of chaos in the three-body problem was the first hint of these limits. It emerged from rigorous mathematical analysis of precise equations. The theorems of Bruns and Poincaré on conserved quantities showed that certain approaches were doomed to fail. The analysis of phase space revealed exponential divergence of nearby trajectories. These weren't approximations or numerical artifacts. They were exact properties of the mathematics describing gravitational interaction. The three-body problem thus becomes a lens through which we see deeper truths about the universe. It's not just a difficult calculation. It's a window into the nature of complexity, predictability, and the limits of knowledge. The same equations that allowed Newton to predict planetary orbits with stunning accuracy contain within them the seeds of their own predictive failure. Add one more body, and precision gives way to chaos. Certainty dissolves into sensitive dependence on initial conditions. Poincaré, working to fix his error in 1889, opened a door to a new understanding of mathematics and physics. Beyond that door lay a landscape where order and chaos intertwine, where determinism and unpredictability coexist, where the universe follows exact laws yet refuses to surrender its secrets. The three-body problem was the key that unlocked this door, and mathematics has never been the same since. Neither has our understanding of what we can and cannot know about the future, written in the motions of planets, stars, and all the complex systems that fill the cosmos. The three-body problem was the key that unlocked this door. Chapter 3. Mathematics as Weapon. Lu Cixin was born in Beijing in June 1963, but spent much of his childhood in Yangquan, a city in Shanxi province, after his father changed jobs. His path to becoming China's most celebrated science fiction author was unconventional. Before writing became his focus, he worked as a senior engineer at a power plant in Shanxi. This wasn't a sideline or a temporary position. For years, Lu balanced the technical demands of engineering with his passion for storytelling, writing 3,000 to 5,000 words daily when time permitted, each novel reportedly taking about a year to complete. The pivotal moment in Lu's childhood came on April 25, 1970, when China launched Dongfang Hong 1, the nation's first satellite. Lu later described witnessing this event as transformative, a deep sense of longing awakening in him as he watched humanity's reach extend into space. Several years after that, he discovered a box of books under his bed in Yangquan. The collection included works by Tolstoy, Moby Dick, and crucially, Jules Verne's Journey to the Center of the Earth. When Lu began reading Verne, his father explained that this was science fiction, creative writing based on science. Lu's persistence as a writer, he later remarked, stemmed from his father's words. But during China's Cultural Revolution, such books could only be read privately. Lu recalled feeling like he was alone on an island, a very lonely state.
This isolation, this sense of being cut off from others who shared his fascination with science and the cosmos, would later infuse his fiction with a particular quality. Liu's reverence and fear of the universe permeates his writing. According to Liu himself, humans will stand in awe of the scale and depth of the universe. His novels focus on curiosity about the unknown, on invoking readers' wonder through exploring futures and possibilities. He also believes that humans should be treated as an entirety, not as individuals, a perspective that shapes the geopolitical scope of his work. When Liu sat down to write The Three-Body Problem, the first novel in what would become the Remembrance of Earth's Past trilogy, he made a deliberate choice that would define his narrative strategy. He would take the unsolvable mathematical chaos that had defeated centuries of brilliant minds and make it the literal engine of an alien civilization's existential crisis. Not as metaphor, not as background detail, but as the inescapable physical reality driving every major plot development. The brilliance lies in how Liu transforms abstract impossibility into visceral, immediate danger. In his fictional universe, a planet called Trisolaris orbits within a three-body system, three suns of comparable mass locked in the chaotic gravitational dance that mathematics proves cannot be predicted. The planet swings through this system, sometimes experiencing what its inhabitants call stable eras, when the sun's configuration produces relatively consistent conditions. During these periods, civilization can develop, agriculture can flourish, cities can be built. But the mathematics guarantees that stable eras cannot last forever.
Without warning, the system transitions into a chaotic era. Perhaps all three suns swing distant and the planet plunges into a freezing darkness where temperatures drop so low that the atmosphere itself begins to condense and fall as snow. Or perhaps one or more suns swing close and the surface scorches under radiation levels that vaporize oceans and incinerate anything exposed to the sky. The transitions between these states occur on timescales of years, sometimes mere days. A stable era might persist for decades, offering hope for long-term survival, or it might collapse after weeks, catching civilization unprepared. The Trisolarans have evolved an extraordinary adaptation to survive these extremes. They can dehydrate themselves, reducing their bodies to dried husks that can survive temperature extremes and long periods without resources. When conditions improve, they rehydrate, returning to active life. This biological strategy allows individuals to survive chaotic eras that would otherwise kill them. But it doesn't solve the deeper problem. Civilization requires infrastructure, agriculture, stable populations. You cannot maintain complex society when the entire population must regularly dehydrate to survive unpredictable climate catastrophes.
Liu reveals through the narrative that hundreds of Trisolaran civilizations have risen and fallen throughout their history. Each time a long, stable era occurs, civilization emerges from the ashes of the previous collapse. Technology advances, knowledge accumulates, cities rise. The Trisolarans understand what threatens them. Their best scientists study the motion of the three suns, attempting to develop an accurate calendar that would predict when the next chaotic era will begin and how severe it will be. If they could solve their version of the three-body problem, they could prepare. They could dehydrate before the catastrophe hits, store resources, build shelters. They could survive not through luck but through knowledge. But the mathematics defeats them. Every model they construct eventually fails. They observe the sun's positions, measure their velocities, calculate forward in time. For a while, predictions match reality. Then divergence creeps in. The predicted position of a sun differs slightly from observation. The difference grows. Eventually, the predictions are useless, and the chaotic era arrives without warning, often with different characteristics than anticipated. The civilization that trusted in the failed prediction suffers additional casualties from being unprepared for the specific disaster that actually manifests.
Liu understood that while mathematicians had discovered rare periodic solutions like Chensener and Montgomery's figure-8 orbit, these measure-zero configurations were effectively impossible to find by chance, making them perfect for dramatizing trisolaran despair. Somewhere in the vast parameter space of three-body configurations, periodic solutions would allow their civilization to survive. But they're not in that configuration. Their system occupies a generic chaotic region, and no amount of fine-tuning can move them to a periodic solution without first solving the equations exactly, which they cannot do. This transforms the mathematical crisis into something intensely personal and political. When the Trisolarans receive Ye Wenji's radio transmission from Earth, revealing our location and our stable single-sun solar system, they see salvation. Earth becomes their target for colonization, not from malice, but from mathematical necessity. Liu makes the invasion inevitable through mathematics alone. Here's where Liu's meritive genius becomes apparent. He presents this through an ingenious virtual reality game called 3-Body. In both the novels and the Netflix adaptation created by David Benioff, D.B. Weiss, and Alexander Wu, characters play a game that transports them to different historical periods, all occurring on a planet in a 3-body system. Players experience China's Warring States period, medieval Europe, the Renaissance, various eras where civilizations rise during stable eras and fall when chaotic eras arrive. The game serves multiple purposes simultaneously. It educates players and readers about the 3-body problem without requiring a mathematics textbook. Famous historical figures appear as characters attempting to solve the problem. Newton teams up with Alan Turing to construct a human-powered computer, millions of soldiers with colored flags acting as logic gates to process calculations about the sun's motion. The attempt fails, as it must. The game level ends with Newton and Turing dying as a chaotic era destroys their civilization. But the game is also a recruitment tool. The Earth Trisolaris Organization, a human group dedicated to facilitating the alien invasion, created the game to identify highly intelligent, scientifically literate individuals who might sympathize with the Trisolarans' plight. The game selects players based on their scientific credentials and social status, then exposes them to the mathematics and the tragedy it creates. Some players, learning of the Trisolarans' desperate situation, decide that humanity deserves to be conquered. Others maintain loyalty to Earth. The 3-body problem becomes a filter, separating those who prioritize mathematical sympathy over species loyalty. The Netflix adaptation, which premiered March 21, 2024, with a budget of approximately $20 million per episode, enhances this with cutting-edge visual effects that make the alien world visceral and real. Viewers see the 3 suns moving across the sky in patterns that defy prediction. They watch civilizations dehydrate en masse as a chaotic era begins, bodies becoming dried husks that will hopefully survive until better conditions return. The stakes aren't abstract. The mathematics drives immediate visual consequences that make the existential threat tangible. Liu's weaponization of mathematics extends beyond using chaos as backstory. The Trisolarans, discovering that humanity is on a stable technological growth curve while they face perpetual disruption, develop sophons. These are protons, fundamental particles that have been manipulated using technology far beyond current human capability. The Trisolarans unfold these protons through higher dimensions, effectively creating 2-dimensional surfaces with enormous area that can be inscribed with computational circuitry. They then refold the protons back to their normal 3-dimensional configuration, creating quantum computers of staggering power embedded in single protons. 4 sophons are sent to Earth ahead of the invasion fleet. Their mission is to sabotage human scientific progress.
The sophons interfere with cortical accelerators, the massive machines physicists use to smash particles together at enormous energies to study fundamental physics. When scientists run experiments, the sophons subtly alter the results, making them nonsensical. Different accelerators produce contradictory data. Theoretical predictions fail to match observations. The laws of physics appear to be breaking down. In the novels and the Netflix series, this leads to a wave of despair and suicide among prominent physicists. Scientists who dedicated their lives to understanding the universe discover that the universe no longer makes sense. Their experiments return garbage data. Their theories collapse. Some, unable to cope with the apparent death of science itself, take their own lives. This is mathematics as weapon in its purest form. The Trisolarans don't destroy human infrastructure directly. They destroy human knowledge, ensuring that by the time the fleet arrives in 450 years, humanity will have made no scientific progress and will be easy to conquer. The protagonist in the first novel, Wang Miao, is a nanomaterials researcher. He experiences the sophon interference firsthand when a countdown appears in his vision, visible to him alone. The countdown doesn't exist in physical reality. The sophons are manipulating his retinas directly, creating phosphorescent patterns that manifest as numbers. When Wang shuts down his nanomaterials research, as the ETO demands, the countdown stops. This demonstrates the sophons' precision and the Trisolarans' commitment to halting specific research they deem threatening.
Liu explores this through character arcs that grapple with mathematical despair. Ye Wenji, the astrophysicist whose decision to respond to the Trisolaran signal sets the entire plot in motion, is motivated partly by her experiences during China's Cultural Revolution. She witnesses her father, also a physicist, beaten to death by Red Guards for his scientific beliefs. She's betrayed by people she trusted, sent to labor camps, and eventually recruited to Red Coast, a secret military base using a massive radio antenna to search for extraterrestrial intelligence. Her disillusionment with humanity deepens when she reads Rachel Carson's Silent Spring, smuggled to her by a colleague who later betrays her. The book's depiction of humanity's destruction of the natural environment parallels the Cultural Revolution's destruction of human lives and culture. This parallel convinces Ye that human civilization is fundamentally corrupt and self-destructive. When the listener on Trisolaris warns Ye not to respond, explaining that revealing Earth's location will lead to invasion, Ye responds anyway. Better to let a superior civilization take over and perhaps create something better from the ashes. The Earth Trisolaris organization that Yi leads splits into factions over how to interpret the mathematics. The Adventists believe humanity should be completely destroyed, that the Trisolarans represent a higher form of civilization deserving of Earth. The Redemptionists believe humans and Trisolarans can coexist, that humanity should help solve the three-body problem to save the Trisolaran civilization without necessitating Earth's conquest. Both factions are responding to the same mathematical reality differently. The Adventists see it as justification for human extinction. The Redemptionists see it as a problem to be solved through cooperation. Shen Yufei, a physicist in the Redemptionist faction, becomes obsessed with solving the three-body problem. Her husband, Wei Cheng, is a mathematical prodigy who develops a novel approach to the problem. They believe that if they can provide the Trisolarans with a solution, a way to predict and survive the chaotic eras, the invasion becomes unnecessary. This hope drives Shen's work until she's murdered by Pan Han, an Adventist who believes that solving the three-body problem would remove the Trisolarans' motivation to flee their homeworld. Pan wants the invasion to proceed, so he kills those trying to prevent it by solving the mathematics. This internal conflict within the ETO mirrors broader questions about mathematics and morality. Can mathematical elegance or scientific curiosity justify betraying your own species? Does understanding an alien civilization's mathematical plight create an obligation to help them, even at enormous cost to humanity? The characters wrestling with these questions aren't caricatures. They're scientists and intellectuals who've thought deeply about their positions.
The mathematics forces them to confront uncomfortable truths about knowledge, loyalty, and survival. The Netflix adaptation amplifies these themes through the Oxford Five, original characters created for the series. Jin Chang is a theoretical physicist who excels at the three-body game. Augie Salazar runs a nanotech company and experiences the countdown when she refuses to shut down research the Trisolarans deem threatening. Saul Durand is a physics researcher. Will Downing is a school physics teacher. Jack Rooney used his physics degree to create a snack food empire. These characters represent different relationships with scientific knowledge, from pure research to commercial application to education. The show depicts how the three-body problem affects each character differently. Jin, the pure theorist, becomes fascinated by the game and the mathematics underlying it. She wants to understand, to solve, to know. Augie, the applied scientist, experiences the consequences of defying mathematical sabotage through the countdown and eventually her nanofiber technology being used in Operation Gazang to intercept the Trisolarans' communications ship. Saul faces despair when his particle accelerator research produces nonsensical results. Will, already dying from a terminal illness, volunteers for a desperate one-way mission to send a human brain as a probe toward the Trisolaran fleet. Detective Shi Chang, nicknamed Da Shi, provides a counterpoint to this mathematical determinism. He's not a scientist. He doesn't understand the equations or the chaos theory. But he understands survival. In one of the story's most memorable scenes, Shi takes Wang to observe locusts. He points out that humans have better technology than locusts, yet locusts survive human attempts to exterminate them. They persist through sheer resilience, adaptability, and numbers. Shi's message is that mathematics doesn't determine everything. Survival requires more than solving equations. The sophistication of Lu's approach becomes clear when you compare it to other science fiction that uses real science. Many authors include scientific concepts as window dressing, adding authenticity without deeply integrating the science into the plot. Lu does the opposite. The mathematical chaos isn't background. It's the entire foundation. Every major plot development flows from it. The mathematics determines character motivations, strategic decisions, and ultimate outcomes. Lu's novel won the Hugo Award for Best Novel in 2015, making it the first novel by an Asian writer to achieve this distinction. This represented a historically significant moment for representation in science fiction. President Barack Obama read the book and described it as having immense scope, noting that it was fun to read, partly because my day-to-day problems with United States Congress seem fairly petty in comparison to the cosmic-scale conflicts Lu portrayed. George R.R. Martin endorsed the book and wrote about its Hugo worthiness on his blog. In 2012, the novel was described as one of China's most successful full-length novels of the past 2 decades. This cultural reception validates Lu's narrative strategy. He took a mathematical concept that most people find dry and abstract and transformed it into compelling drama that resonated across cultures and languages. The three-body problem became accessible not through simplification but through dramatization. Readers didn't need to understand differential equations to grasp that the Trisolarans faced an impossible situation, that mathematics itself guaranteed their doom. The irony embedded in Lu's narrative runs deeper still. The Trisolarans use mathematics as a weapon through the Sophons, but they're also victims of mathematics themselves. Their entire predicament stems from chaos they cannot control or escape. They've achieved incredible technological sophistication, including Sophons, faster-than-light communication, and a fleet capable of interstellar travel. Yet all this advancement cannot save them from the fundamental mathematical properties of their solar system. Technology has limits when the enemy is the structure of space-time itself. This creates a fascinating parallel. Both civilizations are constrained by mathematics. The Trisolarans cannot escape orbital chaos. Humanity, once the Sophons arrive, cannot advance particle physics. Both face limitations imposed not by lack of intelligence or effort, but by the mathematical structure of reality. The Trisolarans have advanced technology, but remain victims of chaos. Humanity has a stable solar system, but faces sabotage of the scientific progress that might allow defense against invasion. Liu's weaponization of mathematics operates on multiple levels simultaneously. There's the direct level, Sophon's sabotaging experiments and orbital chaos dooming the Trisolarans. But there's also the psychological level, how mathematical truths affect human decision-making, loyalty, and hope. When Wang sees the countdown, he must choose between continuing his research or stopping to save his life. When Jin plays the three-body game, she must decide whether understanding the Trisolarans' plight creates sympathy or strengthens resolve to defend Earth. The novel asks whether mathematical knowledge can be neutral. If you understand that a civilization faces extinction from chaotic orbital dynamics, does that understanding create moral obligations? If you possess technology to interfere with another civilization's scientific progress, does the mathematics of your own survival justify using it? These questions don't have easy answers, and Liu doesn't pretend they do. His characters argue, fight, and die over different responses to the same mathematical realities.
The tension between mathematical determinism and human agency runs throughout Liu's trilogy. The first book establishes orbital chaos as an existential threat. The second book, The Dark Forest, explores the strategic implications and introduces concepts like the Dark Forest theory of cosmic sociology. The third book, Death's End, takes the mathematics to even grander scales, exploring the structure of space-time itself. Throughout, mathematics serves as both tool and weapon, enabler and constraint. Liu's choice to weaponize the three-body problem specifically shows his deep understanding of both mathematics and narrative. He could have chosen any scientific concept as the foundation for his story. But this problem offers unique advantages. It connects to fundamental questions about prediction, determinism, and chaos. It scales from planetary systems to galactic dynamics. And it has the narrative advantage of being simultaneously beautiful in its special solutions and terrifying in its general impossibility. The Netflix adaptation, with its massive production values, makes this mathematics accessible to viewers who might never read an equation. Seeing the three suns move across an alien sky, watching civilizations dehydrate as chaotic eras begin, experiencing the terror of unpredictable climate catastrophes, all of this translates abstract mathematics into visceral experience. The showrunners understood that Liu's genius lay in weaponizing mathematical chaos, and they preserved that weaponization while adapting the story for a different medium. Liu Cixin transformed a centuries-old mathematical problem into the engine of existential dread. He took chaos theory's revelation that deterministic systems can be fundamentally unpredictable and made it the reason an alien civilization seeks to conquer Earth. He weaponized mathematical beauty by showing that elegant solutions exist but remain forever out of reach for those trapped in generic chaos. He made mathematics matter in a way that few science fiction authors have achieved, demonstrating that equations can be as compelling and terrifying as any conventional weapon. The three-body problem became, in Liu's hands, a lens for examining deeper questions about knowledge, survival, and the universe's indifference to our desires for predictability. It showed that mathematics imposes limits not just on calculation, but on civilizations. That some problems cannot be solved no matter how advanced you become, and that chaos embedded in deterministic laws creates an unpredictability that can doom entire worlds. This weaponization of mathematics stands as Liu Cixin's greatest narrative achievement, his darkest revelation about the universe we inhabit, and his most compelling demonstration that the most terrifying weapons aren't always the ones we can see or touch, but the ones written into the fundamental structure of reality itself. The three-body problem reveals a profound truth about our universe. Mathematical elegance has limits. Newton's equations, which perfectly predict two gravitating bodies, shatter into chaos when we add just one more.
Poincaré discovered that this isn't a failure of human cleverness, it's the fundamental structure of reality. Deterministic laws don't guarantee predictable futures. Lou Sixon understood this darkness and transformed it into art. By weaponizing mathematical chaos in his science fiction, he showed that the most terrifying constraints aren't technological, they're embedded in the equations governing existence itself. The three-body problem stands as mathematics' humbling monument, reminding us that some questions resist answers not from our limitations, but from the universe's own design. Perfect knowledge remains forever beyond reach, even when the laws are exact. Thank you for listening.